Yeah, I'm thankful for the organizers for this opportunity to tell you about this paper that we posted earlier this week with Sakura Schiffer-Nameki, Apoorv Tewari, and Alison Warman. There were two other papers that were in the same day posted on the archive, which I've listed down here. And I hope to convey today that I don't think we have the full story yet, but we've made a little bit of progress, and there's a lot of more interesting work to be done in this realm of mixed states. So the story is going to be about symmetry TFT approach for non-invertible symmetries of mixed states. So to give a lightning review of SymTFT approach, many of you are familiar with it, very familiar with it, but the basic idea is we're going to study its applications in 1+1D. So if you start off in 1+1D, then in the generalized symmetry story, we can describe the symmetries, the finite symmetries in 1+1D by fusion categories. So we can have group-like symmetries, but we can also have more general non-invertible fusion category symmetries. And then there's a mathematical construction called taking the center, or as a physicist, I construct a string net model. And what this gives you is it takes from the fusion category, gives you a modular tensor category. And so this modular tensor category describes the spontaneously broken one-form symmetries of a 2D, 2+1D topological order called the SymTFT. So in more detail, you start off with a fusion category, which has some pieces of data that describe it, which are the simple objects, the fusion rules, and the F symbol. So for invertible group-like symmetries, this is just the group fusion, the group multiplication, and the F symbol is the anomaly. And then on the other side, for the modular tensor category, we have these anions, which are the simple objects there. They also have fusion rules, but they also have braiding, given by R. And why do we construct a 2+1D theory from a 1+1D symmetry? Well, as has been explained in many papers, especially recently, this kind of framework or approach is very useful for understanding classification of gapped and gapless phases, understanding dualities, detecting anomalies, and then they're especially applicable to non-invertible symmetries to help us understand generalized charges, generalized disorder parameters, et cetera. So how do we apply this formalism to classify gap phases? The basic idea is, as I mentioned before, we start off with this symmetry S in 1+1D, which is the fusion category, and we can construct the center, which will describe a topological order in one higher dimension. And this topological order comes equipped with a canonical gap boundary, which is the gap boundary that realizes the symmetry. What does it mean that it realizes the symmetry? Well, the gap boundary says that certain anion lines can end topologically. And so then you also have anion lines that can't end, and they give rise to low energy excitations at the boundary, and those low energy excitations can describe domain walls of some symmetry. That symmetry is this fusion category S. Okay, so then you can construct theories that have the symmetry. It might be spontaneously broken or partially by choosing appropriate choices of the other boundary. So you can think of this essentially as a 1+1D theory because it's a gapped topological order with two choices of boundary conditions on an interval. It's quasi-1D. And so if, for example, we choose this physical boundary to be the same as our symmetry boundary, we have these anion lines that can tunnel across. They give you order parameters. The symmetry is spontaneously broken. On the other hand, if we manage to find another gap boundary such that the only anion line that's in both of them is the trivial vacuum line, then there's no order parameters, there's no spontaneous symmetry breaking. In fact, there's disorder parameters because these lines that were confined out here can now end at the other boundary. And so this is a symmetric phase or an SPT. But more generally, we can choose many choices of L physical. And so there's kind of a correspondence between the different gap boundaries that you choose for L physical and the different gap phases with the S symmetry. And this kind of construction allows us to construct fixed point Hamiltonians, fixed point states, and understand disorder, order, and string order parameters for generalized symmetries. As a very simple example, we can consider the Z2 symmetry without any anomaly. So this is just Rec Z2 with trivial cocycle. And there, this topological order that you get is Z2 gauge theory toric code. And then, as we know, there are two gap boundaries. There's the so-called Dirichlet boundary condition, Neumann boundary condition, or E or M condensed. And we have the symmetry boundary, which is the E condensed, Dirichlet boundary conditions. And depending on which one we choose for the physical boundary, we can describe the Z2 as spontaneous symmetry broken or symmetric. And you can see that if we instead chose this to have the non-trivial cocycle, then you only have the E condensed boundary. There's no M condensed boundary. So there's no SPT, which is telling you that the symmetry is anomalous. So, okay, this is a general framework that people have applied in 1+1D and higher dimensions to classify gap phases, understand anomalies, etc., pure states. But now the question is, now let's consider mixed states. So a mixed state is the sum over these pure states with probabilities pi. So the sum over the pi is equal to 1, and this is a Hermitian operator. They come up very naturally in many contexts. So for example, when you put a system at finite temperature or when you decohere a pure state, you naturally get a mixed state. And so this is especially applicable recently as people are studying the effects of decoherence on closed quantum systems. You can think of it as coupling your closed quantum system to a bath and tracing out the bath. So these kinds of mixed states have different kinds of symmetries. For example, you can have strong symmetries, and these are just, I've written it for invertible because I have 20 minutes here, but there's similar conditions for non-invertible symmetries. So we have strong symmetries, so then that's the case when rho is an eigen state of U. And so U rho is just some phase times rho. And we can also have weak symmetries where rho commutes with U. You can think of these cases as follows. If it has a strong symmetry, that means that it's an ensemble of states, these psi I, and each of them are symmetric and are in the same symmetry sector. If you have a weak symmetry, then these states are allowed to be in different symmetry sectors because the phases on both sides cancel. So every strong symmetry also gives rise to a weak symmetry, but a weak symmetry may not come associated with a corresponding strong symmetry. And if you start off with pure states, you only have strong symmetries, and every strong symmetry is a weak symmetry. Okay. Now let's run through some very simple lattice model examples. The simplest kind of setting we can have is a 1D spin chain where you have a qubit living on every side. And now you can consider a Z2 symmetry, which just is a spin flip on all the qubits, product of these poly X operators. And now you can consider density matrices that have different symmetry breaking patterns. So for example, if we consider density matrices with strong Z2 symmetry, we can have this strongly symmetric phase. This is just the +1 eigenstate of sigma x on every side. We can have so-called strong to trivial SSV. This is a GHZ state, so it's an all up plus all down state. And it respects this Z2 symmetry acting on the left and on the right side. But it has a non-trivial order parameter, like 2-point correlation of charged operators. So this, you can show it has so-called strong to trivial SSV. These two are actually both pure states. However, the one on the right-hand side is a mixed state. It demonstrates something called strong to weak spontaneous symmetry breaking. It's a projector onto the symmetry even sector. So you can show that it has this strong Z2 symmetry, and you can also show that even though the strong Z2 symmetry is spontaneously broken, there's also a weak Z2 symmetry, as I mentioned before, and that's not spontaneously broken, which we can make precise in terms of order and disorder parameters, et cetera, for strong and weak symmetries. So when we consider mixed states and density matrices, they're not just two phases, we have three phases. We can also consider the scenario where we only have a weak Z2 symmetry. So the density matrix is only invariant if you act with U and U dagger on both sides. In that case, you can have this infinite temperature state, which is weakly symmetric, and you can have this up plus down state, which is weak to trivial spontaneous symmetry breaking. So these two on the bottom and the right one over there are mixed state phases. But more generally, one can ask, how do we systematically classify so-called gapped mixed state phases with possibly generalized symmetries that may be non-invertible? Even before we start systematically understanding the solution to this problem, there are many more elementary problems. So when we're considering these mixed states, you can even ask things like, how do we even define equivalence between density matrices? How do we say two density matrices are the same? What's the analog of adiabatic evolution or connection by local unitary, right? You can also ask, what does gap mean? If I say gapped mixed state phase, what does gap mean? So what is the analog in this context of a gapped parent Hamiltonian? And finally, you can also ask, what are even the consistent patterns of strong and weak symmetries you can have? Because maybe, especially once you get into the non-invertible setting, there's patterns of strong weak symmetries that are not allowed. So what is the analog of like a general consistency condition, set of consistency conditions you want for mixed states? And this has been explored in many works more recently. Almost all of them have been studying invertible symmetries though. Okay, so in our work, we kind of take a particular definition of these first two, so equivalence and gap, and then we just go from there. And there may be different definitions, and all of them might be interesting to explore. But we will take a particular definition of equivalence and gap, and so on and so forth. That will make it easy for us to apply a lot of the tools that we know for pure states and mixed states. Okay, so the definition that we'll take is for any density matrix, you can vectorize the density matrix. So you can construct a pure state in a doubled Hilbert space. This is somewhat similar to in Nikita's talk. I'll draw the connection shortly. So this is called a choice state or a thermal field double. We'll normalize it so it's an appropriately normalized state. And it lives in a doubled Hilbert space. So the original Hilbert space might have be a single spin chain. And then now in this vectorized state, it's a pair of spin chains. And we'll be working with finite symmetries in 1+1D. And we'll just say that a gapped density matrix is gapped if its choice state is the gap ground state of some gapped Hamiltonian. Because the choice state is a pure state, so we can understand it and use the typical kind of definitions. And so this is kind of the starting point we're going to use. And now we can map these strong and weak symmetries into symmetries of this pure choice state. So the strong symmetries will end up being operators that act on one half of the Hilbert space. So the left acting operators on the density matrix will map onto U tensor identity operator. So this U only acts on HL. So the strong symmetries get mapped to operators that act on either HL or HR. The weak symmetries act kind of diagonally between the two layers. And so here, if you look at U rho U dagger, if you vectorize that density matrix, then you end up getting U bar. So bar here is complex conjugation on this doubled Hilbert space. Something that comes automatically in this formalism is anti-unitary swap star symmetry. That just swaps HL and states in HL and states in HR and then performs complex conjugation. So this kind of comes automatically. And I should emphasize that every density matrix maps onto a state in a doubled Hilbert space. Not every state in the double Hilbert space maps onto a density matrix or comes from a density matrix.
Well, in the pure state side at the mapping, the two gaps they are connected, but that not means on density matrix side, the two density matrices are connected.
Yeah, so equivalence relations on the density matrices versus equivalence relations on the choice states or canonical purification, that's a more subtle question. And especially more subtle in higher dimensions. But in 1+1D, this seems to be okay to try to just use this definition, at least for fixed points. Okay, so this caveat is really we should be working with something called the canonical purification, which is what Nikita mentioned. But we're going to be really looking at fixed point states where rho, for example, is a product of commuting projectors. And so then the canonical purification is the choice state of square root of rho, but rho is just proportional to square root of rho. So everything is okay if we just work with choice state. Okay, so now suppose that we have just strong symmetries. So there are no inherently weak symmetries that don't come along with their strong partners. In this case, we have kind of a doubled symmetry in the doubled Hilbert space. So we have an S cross S bar symmetry. So the natural thing to try to do is to construct a symmetry TFT, a SymTFT for S cross S bar. And so now we have two layers, left and right, and we still have a symmetry boundary, which just gives you this S cross S bar symmetry on the left-hand side. And again, you can ask, oh, and I should mention that because we automatically have the swap star symmetry, you should really think of this as a symmetry-enriched topological order. So you not only have the anions, but you also have a global zero-form anti-unitary swap star symmetry. And so now you can try to plug in the previous machinery where we just try to construct all the L physical and try to classify gap phases by the L physical. However, not all physical actually furnish consistent mixed state gap phases. And so that's the whole difficulty of this problem.
So because SymTFT should equate with another Z2 symmetry, which is important, that you mentioned swap symmetry.
Yes.
That's another requirement.
Yes, and this swap star symmetry will be very important in how we choose the L physical. Right, so let's give an example. So I mentioned not all physical Lagrangian algebras actually furnish consistent mixed state phases. So why is that the case? Let's look at the strong Z2 symmetry example. So in this case, the symmetry is just going to be Z2 cross Z2. So the SymTFT is going to be Z2 cross Z2 gauge theory. And the anions are generated by this E left, E right, M left, M right. So these are the gauge charges and gauge fluxes for the Z2 cross Z2 gauge theory. And these on the right-hand side are all of the Lagrangian algebras. In this case, it's just abelian, so you can also just work with Lagrangian subgroups. And so all these are just collections of anions that have trivial mutual braiding or bosonic, etc. They describe gap boundaries of the Z2 cross Z2 gauge theory. However, as we saw earlier, there are only 3 phases with the strong Z2 symmetry. There's this one, which is the L2, is the completely symmetric phase. The second density matrix is L1, is the completely spontaneous symmetry broken phase. And then we also had the strong to weak SSB phase, L3. So you can think of, on the L3, it describes spontaneous symmetry breaking of the Z2 cross Z2 down to the diagonal Z2. So the diagonal Z2 maps onto the weak Z2, which is why it's not spontaneously broken in this case. So then you can ask, what's wrong with these other 3 Lagrangian algebras? And so what you have to consider is, as I mentioned before, every mixed state maps onto a state in the double Hilbert space, but not every state in the double Hilbert space is comes from a density matrix. And so there are constraints on the density matrix. It's Hermitian, and it's also positive semi-definite, right? All these PIs are probabilities. And so those 2 constraints put constraints on the physical Lagrangian algebras. So this hermiticity ends up being a swap star symmetry on the Lagrangian algebra. So if, for example, A left, B right occurs in your Lagrangian algebra with some coefficient, then the swap star of that, which is B left bar, A right bar, also has to be in the Lagrangian algebra with the same integer coefficient. Positivity is a more subtle condition. So to derive this guy, you have to use patch operators and the ability to take square root of rho, et cetera, Cauchy-Schwarz inequality. But this is kind of the condition that we get. And you can see that these bottom 2 violate hermiticity because they're not invariant under swap star. Swap star will take E left to E right. But you see that there's no E right in L5. L4, of course, is more subtle. So E left, M right comes with E right, M left. So it is swap star symmetric. However, it violates, you can check that it violates this positivity condition, because this positivity condition, basically what it does is it bounds the kind of off diagonal guys by the diagonal guys. And here you don't have an E left, E right. You don't have M left, M right. So the right-hand side here is actually 0, but the left-hand side is 1. So it violates the positivity condition. And so our conjecture is that these are necessary and sufficient conditions to furnish these so-called mixed state Lagrangian algebras, which correspond to valid choice states. That's if you start off with only strong symmetries. But what if you have a combination of strong and weak symmetries? What are the consistent patterns of symmetries you can get in that context? So the proposal that we have for constructing these valid patterns of strong and weak symmetries is we first take an enlarged symmetry, which does have this factorization form of S cross S bar. And then you can consider the condensation of a condensable but not maximal Lagrangian algebra, or a condensable but not Lagrangian algebra, which is basically just a condensable algebra composed of diagonal charges. And physically what this is doing is it's explicitly breaking the strong symmetry down to weak symmetry. So what this does is it creates a domain wall between your original topological order and a different topological order that's smaller. And because it's a smaller topological order, it also comes from a smaller symmetry. And that smaller symmetry is there because you've explicitly broken some of the strong symmetry to weak. And so a simple example of this in the non-invertible setting is if you take S to be like Z2 Tombar-Yamagami Ising, then you can start with Ising, double Ising cross double Ising. You can condense some diagonal charge and you get the center of Z2 cos Z2 Ty. So for the experts in the room, that's actually the rep H8, center of rep H8. And so you can see the Z2 cos Z2 Ty, it doesn't factorize into S cross S bar. But you can think of this physically, what it's describing is a density matrix that has a strong Z2 symmetry and a weak duality symmetry. And we can write down density matrices that demonstrate those patterns of symmetry. On the other hand, if you try to have a strong duality but a weak Z2, that's not a consistent pattern of symmetry. And that's also related to the fact that there's not a condensable algebra that will give you that pattern of symmetry. You can't condense, basically you can't condense 1 plus sigma, 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 sigma. That's not condensable. Okay, but this is one way we can construct consistent patterns of strong, weak, non-invertible symmetries. So as I mentioned before, we have some conjectured necessary and sufficient conditions for the case where you start off with a strong symmetry. The case where you begin with strong and weak symmetries and this extension and partial condensation, that I don't think is as rigorous footing. We don't have it on as rigorous footing. We have an approach for constructing consistent strong to weak symmetry patterns, as I mentioned on the previous slide. And we also have constraints on the multiplet of degenerate states that come from spontaneous symmetry breaking. And I can say exactly what the physical meaning of that is if you have questions. And then there's also lattice models that we can construct using the SymTFT approach, similar to these kind of anion chains. And examples of various interesting kinds of phases, including strong to weak SSB with non-invertible symmetries, mixed strong weak non-invertible SBTs, and also some cases where patterns of non-invertible strong weak symmetries give rise to interesting anomaly-like constraints based on the Hilbert space that I can also discuss if there are questions. There are many things that we don't understand. So we conjecture that these are necessary and sufficient, but we don't have a proof, although I can mention an idea for a route that one can use to prove this condition. But we haven't worked it out in complete detail. In particular, also this condition, on the slide, I wrote the left-hand side without the square. That's all we can prove. But there's reason to believe that it also holds with the square on the left-hand side. So the stronger condition holds. But I don't know how to prove it, and we also don't have a counterexample. So there's maybe room for improvement. And then we also can ask the question, this kind of starting off with a larger symmetry, condensing diagonal charges, does that give you all the patterns of consistent strong and weak symmetries? We don't have a proof of that, but it seems to give a large class of them. We can also study gapless gap phases, phase transitions, higher dimensions, higher form symmetries. These mixed states have intrinsically mixed entanglement properties that are interesting to study. And one can also ask questions about anomalies, physical implications, enforced gaplessness, things like that, that I think are interesting to explore in the future. With that, I thank you for listening to the talk.